This video is going to cover scientific notation, just kind of the intro, and then changing back and forth between regular decimal form and scientific notation. Okay? So scientific notation is used when numbers are really, really big or really, really small. What's good about it is you can tell at a glance the magnitude of a number. Okay? And so it's easy then to compare it to another large number or to compare two really small numbers. Right? When you write big numbers like the two I've written in decimal form, you can sometimes draw the wrong conclusion because sometimes your focus is on the 38 and the 12, and 38 is bigger than 12, and you just see a bunch of zeros. Okay? So it's kind of hard to compare those two numbers. They're not written above one another where you can line everything up. So on this one, it might be good to double check by maybe putting in the commas for every period, right? So a comma to make the thousands, the millions, and all that. And then when you take a look at it, you can see that you've really got, let me mark it here, this 380, this 1200. You can really see that the one on the right is actually bigger. Okay? Now we're going to talk about scientific notation, but I'm just going to show you what these turn out to be. Currently, the decimal would be understood to be after the number. Whole numbers, the decimal is understood to be after the ones place. So this one right here would be 3.8, and I'll talk about how you do this, times 10, and it would be 6, 9, 10, 11, times 10 to the 11th power, where this one would be 1.2 times 10 to the 3, 6, 9, 10, 11, 12 to the 12th power. Okay? And then just with a quick glance at that exponent, I can tell that that second number is bigger. It's a whole magnitude bigger. So when you're looking at things like the distance from here to Mars, or when you're looking at small stuff like how big things are inside a human cell or on these modern day microchips, those numbers are extremely big or extremely small. Okay, so scientific notation is what we can use. Scientific notation enables us to write them so that the size, the magnitude of the numbers is more obvious. And then we'll also find later that you can do operations with numbers in scientific notation a lot easier, in a very easy way. All right, so to get a number into scientific notation, you have to understand what scientific notation, what the form is. So it has to look like that, some number times 10 raised to a power. This power will be either a positive integer, okay, like 1, 2, 3 on up, or it'll be a negative integer, like a negative 1, negative 2, negative 3. Which one it is depends on the original number. The exponent is going to be a positive integer if the number was big. Okay? And it's going to be a negative integer if the original number was small. I want to give you a way of changing back and forth between decimal notation and scientific notation without memorizing whether you should move right or left. You just need to do something that's sensible, and you'll see what I'm talking about in a minute. Now, this first part, that needs to be a number like 5.7. It needs to be a number where there's only one place to the left of the decimal, which makes that number be something that's less than 10 and then it can be bigger than or equal to 1. All right, so we want just one place to the left of the decimal. And that's one way we can say that. We need the number part to be between 1 and 10, but it could be just a 1. Now the thing is, a number could be negative, so it rarely is, but it could be. So I'm going to put absolute value on that. So the number part, the size of it, needs to be between 1 and 10. Okay? So you need one non-zero number over here, is what that's saying. To the left of the decimal. No more than one decimal. Okay. All right, so it'll make more sense when we do it, when we use scientific notation to rewrite these. So if you have a whole number, the decimal's understood to be there. But we want the decimal to be here so that there's only one number to the left of the decimal. So the number part, remember how it was a times 10 to the n? The a would be 6.318. And then I'm going to multiply by 10 to some power. And since that's a big number, it's going to be a positive value. And what it is would be how many places you had to move the decimal. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 places. So I'll be multiplying that by 10 to the positive 9, 10 to the 9th power. Now the reason that works is if you had a number, let's say you had 51 or 5.1. If you multiply that by 10, that's going to wind up being 51. If you had 5.1 and you multiplied by 10 to the second, so that's 10 and then another 10, that turns out to be multiplying by 100, that turns out to be 510. Notice how here the decimal would have moved once, here it would have moved twice. So the shortcut for multiplying by a power of 10 is that the decimal moves once for every time you're multiplying by 10, or for the number of zeros. So if I multiply by 100, I move it twice. If I were multiplying it by 10 to the 5th, multiplying by 110, and then another 10, another 10, another 10. I've multiplied by 5 tens, that number is going to wind up being this. Okay? So that's the idea behind just counting how many places the decimal actually moved to determine what the exponent would be. Now see how the second number is small? And the decimal is explicitly right here, but I need it to be right there so that there's only one place in front of the decimal. So the a part of this is going to be 7. And then how many moves I made? 1, 2, 3, 4, 5, 6. The decimal moves 6 places, but the number's small, so we're going to say -6 on that. All right, now this is a relatively big number. The decimal is understood, since that's a whole number, the decimal is understood to be after that last 0. Okay, I want it to be here, so there's one place to the left of it. So the number part would be 9.3. And then how many places you moved would give you the exponent. And you know it's going to be positive because the number was big. So that's 3, 6, 7 spots. It would be 9.3 times 10 to the 7th. Okay, this one's small. We know our next exponent's going to be negative. Exponent is here, but we need it to be after the 3, so we have one place to the right of the decimal. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 moves and it's going to be 10 to the negative ninth since the original number was small. All right, so that's changing from the decimal form into the scientific notation. Okay. Now, you sometimes have to go the other way with it. You have to start with it in decimal form and then, or start with it in scientific notation, and then get it into decimal form. So what works well for that is to write down the number part. Then notice that you have a positive exponent. So that means you should wind up with a number that's big. So you don't want to move your decimal this way because that's going to be making the number small. So you know you're going to wind up coming in here and multiplying by 10 8 times. Every time you multiply by 10, it's moving the decimal one spot. So you're going to need to move it 8 times. 2, 3, 4, 5, 6, 7, 8. Then any of these bins, any of these open spots, I'm going to fill in with zeros. And then I'm just going to clean it up so that people can see what it is. So with 5 zeros, 2, 3, 4, 5. And then it helps to put in those commas so people can see, can read better what that number turned out to be. So it turned out to be 419,200,000. All right, now here I have a negative exponent, so I know this one should turn out to be a small number. So you're going to start by writing the 6.07 down. And then you're going to think about which way you should move. If you move this way, you're making the number big. So since it was a negative exponent, you need the number to wind up being small. So you're going to move this way. Okay, I need to move that over a little bit so I can show that better. Okay. All right, so it was a negative exponent, so I know my number needs to be small, so it makes sense to move this way. 1, 2, 3, 4, 5 places. And then fill those openings with zeros that you made. And then clean up what your answer is. It's 0.0000607. And you normally, with decimals, it's good to put that 0 to the left of the decimal so people know that was an intentional decimal. Okay. Make it explicit there. Okay. All right, now one more thing before I do the operations with numbers in scientific notation. All right, when you have these powers of 10, there are certain ones that turn out to kind of reach a milestone. So like 10 to the third would be 1,000. 10 to the negative third would be 1,000th with a TH. Okay, 10 to the sixth makes a million. 10 to the negative 6 makes a millionth. Okay, and then here 10 to the ninth, that's a billion. And then if I had 10 to the negative 9, that would be 0.123456781. That would be 9, 1, 2, 3, 4, 5, 6, 7, 8, yeah, 9 places. Okay, before you have your decimal followed by 9 things, that would be a billionth with a TH. All right, and then that one, that 10 to the negative 9, that comes up kind of a lot these days. That's the same as using a prefix nano later. Like you might have something that's 3 nanometers, for instance, in length. And nano means it's billions. So if something is 3 nanometers, it's 3 billionths of a meter. Okay, so really tiny, things that microchips might have. Okay.